back in February this year, we ran headfirst into a very complex yet very common problem, metadata at scale. Hi everyone, I am Arnav. I work as a performance and research engineer at E6 Data, which is another data lakehouse compute engine. And in this session, I am going to walk you all through our journey and also the lessons learned while tackling an iceberg table with tens of millions of files. So yeah. 45 million active data files and 5 TB of metadata log. This is the exact problem that we ran headfirst into. So on paper, data lakes sort of scale infinitely, and but in practice, often there's a silent bottleneck, the metadata. So you have probably heard it too, right? Modern data lakes promise infinite scalability. We believed it too until someone actually started dictating what we could do and what we couldn't do. So the 5 TB of metadata that you see here is the actual problem and not the 50 TB of data. The 5 TB of metadata that we had for this particular table was spread across some about some 200K metadata files across manifest lists, manifest files, and all of that. And this talk is going to be about that metadata, how it explodes, when it explodes, and why like naive metadata reads and scans can break your query in terms of performance and all. So before that, let's talk about how and why we sometimes underestimate metadata itself. Because in theory, what we believe is metadata is really, really lightweight. But actually, in practice, what happens is, at a scale, when you have tens of millions of data files, your metadata is also not lightweight anymore. It can blow up, right? Another thing that we believe is pruning, right? Pruning is a simple min and max, techniques. You do simple checks and eliminate all the files. But at this scale, again, of very big metadata, what happens is you can't simply load all of these stats into your memory to do the pruning. So pruning, then loading everything in memory becomes a very naive decision to take. Another thing about snapshots and manifests is like we believe that they are very cheap and they are the best way to time travel and have versioning to our data, to our queries and all of that. And we associate the cost of having this metadata overhead to storage sometimes, right? But actually, in reality, for such append heavy workloads, the real cost of metadata is not in that storage, which is cheap, but it's in the memory and compute that it takes in the query engine itself. So what we have so far learned is like file counts rather than the total aggregate file sizes is what will kill your queries or execution of those queries. And all the rich structure, like the manifest files, manifest lists, all of that, will only help you if you properly stream it and not materialize all of that into the memory. And the real cost of metadata is not storage, it is the memory during the planning. So yeah, we have all seen this rich metadata structure for Iceberg, and we are all big fans of it. And what we believe is these manifest lists and extra overhead that Iceberg will add, it's very lightweight, right? But the design that we just saw assumes like manifests and all of these are very compact. But what happens, as we just saw at the scale, with every additional file that you add, it creates a corresponding metadata entry. Think of business trends like event streaming pipelines, or those are like your Kafka and Flink jobs, continuously appending small batches of files, or your transactional logs for that matter, like financial systems or clickstream data, or the IoT data, which will feed events every hour or so, or the data ingestions from SaaS APIs, all of that. So all these append-heavy pipelines will create millions of small files to maintain the real-time analytics. And over time, these snapshots will balloon up, and your data is still manageable, but the metadata footprint has grown so much that you can't possibly fit it into memory and read it. um, to visualize all of this better, I often think of the extreme case, right? Which is mostly hypothetical, but just to get a better understanding of this. Think of a workload where you are ingesting just one row every single time. So for that one row, what you also add is the metadata. Those are your statistics, the column statistics and all of that. Imagine you have some 5 to 10 columns. For every column, you will also add the corresponding min and max values. So for each row of data added, let's say it's 1 KB, you are adding almost more than 2 KB of metadata itself. This is, of course, hypothetical. This is extreme, and no one would do this kind of workload. But this is just to realize how the ratio can keep growing. But in reality, when we encountered this particular problem, what we saw was this particular table that we were dealing with in its lifespan started with a ratio of about 1 to 2%, and the ratio of this metadata to data went all the way up to about 9 to 10%, just in the matter of a month or so. So this is actually the kind of problem that we can face in real-world production workloads. So a lot of us will also argue that things like compaction and optimize and all of these, right, will solve for this particular problem. But the point of view that we are looking at this problem today is from a data lake point of view. When we talk about all these open table formats, Iceberg and Delta, we talk about the notion of interoperability and no vendor lock-in. So here in such kind of data, especially for us, when we offer like E6 data as an engine offers, like you can start querying your workloads without any migration from Databricks to Snowflake. So we, as an analytical query engine, don't have control over the data in itself, right? So optimize and all of that can, of course, solve this problem for you, but those are for your data warehouses like BigQuery and stuff like that. And also sometimes this might actually be the case, right? You don't want to spend a lot on your optimized compute, so you end up with such a situation, such a high metadata to data ratio for a long period of time before you do the optimize, that is. So yeah. Yeah, so these memes actually capture the exact pain point we felt. It was not the table size that was throttling our engine, but it was actually the metadata that did, because historically, like since a couple of years, we are able to deal with tables of size of hundreds of terabytes. But this was only the first time we were throttling to deal with a table that was about 50 TB of data, right? So metadata, again, was the actual bottleneck, not the data. Now, this metadata explosion problem can have different symptoms for different systems. It can look different. So what happens is, even before the query execution starts, a query engine would want to read all of these statistics to plan better, to know which files to actually read, which files to actually skip, and all of that. But that's where the system can actually tip over before even reading a single data file, right? So metadata here can become the largest cost of your query, not the actual data reading, in terms of latencies or in terms of compute or in terms of memory as well. For us, this particular problem looked like we saw this problem like an out-of-memory issue. So for us, if you can see the graph, we still have enough compute available with us, but our metadata reading system or metadata reading service started to blow up in terms of memory all the way up to 500 GB. And that's where I think we were able to read about half the data files, like the statistics of half the data files, like 22 million data files. And then it just kept tipping over, and the crash loop just kept going on and on. So Yeah, when we try to load every manifest entry or all the manifest files that are available out there to, better plan the query, this is what happens. And scaling hardware, of course, is not always the solution. There are other considerations that come with it, right? Like cost and everything. The bottleneck here is actually more logical than physical. Even though it looks like a physical bottleneck, it's a logical one. So, yeah. Now, let's talk about how we dealt with this particular metadata explosion problem. And to deal with, I think we simply changed the approach in which we looked at the metadata itself. And that's how we landed on 3 key ideas, right? Number 1, streaming metadata reads. So instead of materializing everything, we stream manifest files and manifest entries and all of that in bounded chunks, right? The second approach that we took was layered pruning. So we prune at manifest level first, and only then later on we do the file pruning and then all of that. Finally, and I think the most insightful or the most important approach that we took was to treat metadata as a first-class data citizen itself. So once you are able to model your metadata as data, you unlock a whole bunch of optimizations that you have already built for your query engine. So yeah, I'll go into each of these in detail, but high-level idea is to stop treating metadata as an afterthought, but treat it as a first-class workload for your query engine, right? So let's look at this small example here, the example that we are talking about, 45 million active data files. So what would that mean is, and OK, this was a white table, by the way, like I think about 100, 200 columns, somewhere in between 100 and 200. So for 45 million active data files, even if you take an average of 10 to 15 KB of stats, now your stats as your upper bound, lower bound, null counts, and all of that, that would mean, that would translate to more than 500 GB of memory, as we just saw in the previous slide. So you can't possibly load all of that into your memory, and that's how we came across our key actions. One, that is, don't load every manifest file into the memory, and then smartly use these manifest summaries that are available to decide what to open and what not. But we'll dive into it a little later. Then what we also decided was to stream all of this metadata in batches so that we don't end up with stuff like and all. And always that way, we are keeping our memory bounded and predictable. Now, just by doing this streaming, we solved the problem of our metadata reading service going out of memory, and we could get the results. The query was working fine and all of that. But our latencies of these queries on top of this table were still not good enough, right? So we took some other steps to further solve this problem. The brute force way was, very obvious that we just saw, like streaming all the metadata instead of loading it. But also, that is because there's one key insight here. Like most of your planning optimizations that you do in your planner won't need all the metadata in the memory all at once. You might need all of the metadata, but you don't need all of it all at once, right? So that was a key insight that we got from it. And there's one very important thing, like the Iceberg spec will give us some sort of hooks and different how it's modeled the metadata, which we can leverage very well to do this sort of streaming. And we'll actually, let's dive deep into how we can do that. Yeah, coming to our approach or core idea 2 to mitigate this particular problem, we developed some sort of hierarchical or layered pruning approach. If you see in this diagram here, on the left-hand side, you see a manifest list. So every snapshot that you're trying to read will have exactly one manifest list associated with it in the Iceberg model. But these manifest lists, what they also have is partition summaries. which is basically the statistics of all your partition columns. So again, the upper bound, lower bound, the null counts, non counts, all of that for each and every partition column. So that is what you can leverage. So even before reading a manifest file, you have completely eliminated the need of reading it just by pushing your query predicates. Like your query will have some predicates. You can push that to this manifest file level reading, and you can eliminate a whole bunch of things. Now, we just talked about the partition summaries that are available. They have these ranges or something like that's a lower bound, upper bound, right? And our query predicates will have the qualifying partitions that we need for a particular query. So using both of them, we sort of came up with an intelligent yet compact mapping, which told us, like, for every given manifest files, what are the plausible partitions that it will qualify, right? So yeah, let's see how we can use this mapping further. So this is the same mapping from the previous slide. What we saw was in the previous slide, or the previous first step of the layered pruning, we did sort of partition pruning at a manifest list level. Now, what we are going to do is partition pruning as well as the file pruning at a much deeper level, that is at a manifest file row level. So the mapping that we created in the previous slide, we used that mapping for intelligent queuing, right? So what naive implementation can do is we have a whole list of manifest files now ready for us to read. We read each and every manifest file, and we make a partition to active data file kind of mapping in order to further actually read the data files. But what we did was we built some sort of priority queue, let's say, to promote some manifest file reading over the other, so that we exhaust reading of particular partitions first, or specific partitions before others, so that the moment we have exhausted reading all the manifest files for a particular partition, we can promote that particular task further. So that is one key highlight there, like intelligent queuing that we built there. And now, as you can see, like the manifest file streaming reads and all of that are bounded. And once you read a manifest file row by row, you can read the stats, you can do the pruning, and that's also the step where you discard all of the stats because you no longer read them and you keep the memory bounded. So yeah, these are the two things. And of course, the third level of pruning is your row group pruning and everything that you can do with the footers that are available for these data files. But that, of course, comes later when you actually read the data files. Now, the third core idea that we built our system around was, and I think this is the most important one again, like treating metadata as a first-class citizen or first-class data itself. So in essence, if I were to summarize, what I would say is, for every single query that you fire to the engine, you would translate it to almost two independent SQL queries. One that you apply on top of your metadata, and the other one that you apply on top of your data after consuming the results from the first query. So yeah, this approach I think we took because there was one thing that we realized. There was a missed opportunity cost in some of the manifest files which had 0 qualifying rows, and we were still reading it, even after doing the earlier partition level pruning after reading the manifest summaries. Even after that, there were some files, manifest files, which were reading, but after reading those files, we realized, okay, there are absolutely 0 rows qualifying. So in order to further improve the performance, this is how we approach this particular problem. This is a great example on how you can model, or this is an example to prove that you can model your metadata reading part to a SQL query itself. So let's say there's a query in front of you which is doing some select, some projections, and it's also having filters on top of the partition columns, and some filters on some particular columns using the upper bounds and lower bounds, and you do the order by on the partition summaries that you have for further optimizing, and finally group by to create the partition to part file mapping, which you will later use for reading. So after modeling this, what we essentially unlocked were some fundamentals of query engine optimization. So all of it, right? Your projection push down, your filter push down, your different types of caching, the parallelism and the distribution, all of that simply just by modeling the metadata to SQL data queries without building extra stuff specifically for metadata. Like that, I think that's the key insight here. What this unlocks is, of course, manifest level skipping, reject entire manifest files early, and now also use the other optimizations that you build. It can be anything. You can build indexes. You can use your Bloom filters or materialized views, and stuff like result set caching and data caching. Absolutely everything or almost everything that you have built for your query engine without having to make special operators to handle metadata itself. So yeah, I think we are towards the end of this. I would just quickly like to summarize what all things that we saw today. So what we first saw was high frequency append heavy ingestions can grow and explode the metadata very fast. So initially, even if you feel like, okay, I'm doing real-time querying and I'm ingesting very fast, initially your querying performance might still look good, but over time the metadata will balloon up and your performance will start degrading. Query execution often struggles from high data file counts, not the data file sizes, because more the number of files you have, more the metadata, associated metadata that you have to deal with. In terms of solutions, what we first did was we materialized, instead of materializing all the stats into memory, the key insight we had is you don't need all of the stats in the memory all at once. And leveraging this insight, we started streaming the stats. And progressively, to narrow down the search space, we built a hierarchical or layered pruning approach. And finally, we started treating metadata as data and used our already in place advanced SQL optimizations to take care of this metadata now. So on my concluding remarks, I would just like to say metadata isn't an overhead. It's a really useful data set if you know how to use it. So yeah, thank you so much. I think we can take questions now.
I just had a quick question. So, do you have to wait for a certain amount of metadata to be a batch before you send it over, or if you wait for some time, then you'll always send it over? Otherwise, do you ever experience any more replication lag, for your streaming?
Yeah, so earlier our implementation did not do streaming for metadata. It read all at once in the memory. So that was, you have to wait for all of it to get materialized, and your materialized metadata view will explode. But once we started doing this, we built the intelligent queuing that I talked about, right? So that's why we qualified certain or prioritized certain metadata manifest files before others. That way, there was early promotion of tasks as possible. So let's say for every given partition, I complete reading all the possible manifest files, so that I don't have to wait for any other manifest files because I certainly know that I have exhausted reading all of this. So that is how we try to deal with what you just talked about. Does that answer your question? Yeah. Got it.
So you talked about the techniques, which is fine. So what does E6 data offers? Do you offer an engine to do that, or like where does it fit in?
Yeah, so E6 data is like a whole data lakehouse. It's a query engine. So let's say you have your existing workloads on Databricks or Snowflake. So you don't have to migrate any of that into our engine. Obviously, it's your data. It's in your S3 object store or wherever it is. We directly plug into that. We plug into your object store, and we offer a full-fledged analytical querying engine. So E6 data is like a query engine in itself.
So you understand the Iceberg REST catalog and everything. So
Yeah, that's right.
Okay, it's another. You can use it as another engine.
Yeah. So I think in terms of catalogs, again, this whole data lakehouse system is built around the notion of no vendor lock-in. You plug and play. So we also support like all kinds of catalogs that you have. If you are Unity, that's fine. If you are Hive Meta, so that's also fine. So we can directly plug into that catalog your existing object store and start querying right from there. And what we have also very recently built is an ingest engine that we are soon going to launch. But I think with an ingest engine and with the query engine, both of them in place, we'll much better be able to handle such problems of small files, because now since we control ingest also, we will run those optimize and compaction jobs and all of that.
So this is a querying engine, right? And you said you are working on an ingestion engine. So this querying engine, does it impact the write? Since you are touching the manifest files and all, right? So when the write operation is going on, like is that being affected?
Not at all. And it's true for any engine, actually, not just E6 data. Any query engine, the Iceberg model is made such that your writes are not affected even if you are querying, because you have the at the toppest level of your hierarchical tree of Iceberg, you have that metadata file, which has a pointer to your latest snapshot. So only once when you are done writing the entire snapshot or the new batch, basically, only then your meta store will tell you, okay, now the snapshot has changed. This is the new metadata file, and this is the new hierarchical tree of Iceberg. So yeah, it absolutely doesn't affect the writers while we do querying. But that is also why we run into such problems, like not speaking about E6 data, like in general, all the query engines face this small file problem, or optimizing the data file size problem, just because of support of this particular feature wherein you can do snapshotting.
Okay, yep, thank you.
Last question.
Hi. If I have the optimization running regularly on my tables and I'm doing the expiry snapshot, then where will this thing then fit in? Because I may not retain all the snapshot for my entire Iceberg table history, right? I may maintain only, let's say, last 5 snapshot or 1 week of snapshots, and then optimization can help in compacting the metadata and reducing the size of the manifest files and all.
Yeah, you are absolutely right, and I think that is how this particular problem should be solved, in a data engineering way rather than a query engineering way, right? So, as I mentioned earlier, data warehouses, or like let's say BigQuery and all of that, they can very well control this. Like they can control the compaction and all of that, because they are in control of your data. But for data lakehouse such as E6 data, it won't control how your data is present or how your data is modeled. So it's customers' data, and as a query engine, we don't have control over compaction or optimized computes, right? So yeah, that is why we have to deal with whatever is thrown to us, basically. And another thing to note is, this particular explosion can happen between your two compaction job as well. So just between, let's say you do compaction job daily. Now this problem, maybe not to this particular extent, but to some extent can happen even if you do compactions daily. between the start and end of your compaction. And yeah, like this can happen there also, and you have to deal with it. Yeah. I hope that answered your question.
Thank you so much, everyone. Let's give them a round of applause.